Okay, it's time to begin. So welcome everybody to the first ITGilde Guru class. Let's just spend 1 minute to tell you about ITGilde Gurus. The idea is that I'm from the Netherlands myself, and I work with amazing people here in the Netherlands who are experienced all in their specific topics, and I wanted to do something together and to reach out to the outside world as a team, because I have my things, but the people from the Guru team like Gabor and Pascal and the other guys, they have their specializations as well. And as everybody has their specializations, I think everybody has something to offer to the world. And that is why we started this new initiative. And the new initiative is ITGilde Gurus. And the idea of ITGilde Gurus is that we are going to share lots of amazing topics. It's my honor and pleasure to be the first one who is presenting. I think some of you might know me already, maybe some even personal, others maybe online. No matter how you got here, it's my pleasure that you are here. I would like to give a quick overview of the options to communicate. We are a small group today, including myself. At this moment we are 6. And that means that there is room for discussion and so on. I would like to ask you if we can use the chat as the first line of discussion. So if you have anything to ask or anything, just put it in the chat. If for any reason the chat is not working, let's do audio. Yeah, just open your microphone, say something, and I will definitely hear activity coming in. And that should help us to get through this session. This is a short session. We are trying to make ITGilde Guru sessions short and to the point and very focused on specific topics. So this is a 2-hour session, and in these 2 hours we are going to talk about Linux memory and nothing but memory. In order to present this session, I have made some slides. I'm not a big fan of slides, but slides do offer the advantage that they allow you to go through topics in a reasonable amount of time. So I am going to share access to my slides, and that is going to happen right now. I will share the slides with you through the course resources as well. When I do slides, I always work on updating the slides until the very last minute, so I have not yet updated them at this moment. So slides, where are you? Here is the slides. You should be able to see that right now. I'm always trying to indicate what I expect you to see in your interface, and you should see amazing PowerPoint with my slide presentation about memory. For your information, this presentation is coming from a course that I have recorded for Pearson. The title of the course is Linux Performance Optimization. I recorded that 2 years ago. And there is a lesson about memory, and I updated that lesson to 2020 standards so that everything matches current environments. Of course, I'm not just going to do slides. I also have access to a couple of machines, a physical machine and some virtual machines. For everything that is directly related to the Linux kernel and the way that the Linux kernel is interfacing hardware, I can recommend that you use a physical machine because physical machines offer full functionality, and some of the functionality goes away in virtualization. Some people ask, hey Sander, you have a preference for VMware as a virtualization platform? Nice to know in this context is that VMware, in my opinion, is the virtualization platform that goes furthest in offering advanced features that are interesting when you are sitting close to the Linux kernel, when you want to do optimization and stuff like that. So I prepared my my machine. Let me already prepare an SSH session to the machine so that we don't lose any time later on. You cannot see that I'm doing that. I'm just doing that for myself so that later on the machine is ready to go. Oh, that is a Fedora machine. Just upgrading my Fedora 31 to 32. Fedora in SSH does not provide root access by default. I'm not taking the trouble of showing you how I am SSHing into a remote machine. Just expecting that that is stuff that everybody knows about. Oh, and now I need to use the appropriate username. I will get there. And let's not waste time on this now. I will multitask to figure out why I cannot log in to my remote machine. Right, a little bit about you. I expect you to be familiar with the Linux operating system already. This is not a beginner class in Linux. This is an advanced class. It's a guru class, and that means that I expect you to have a reasonable experience with the Linux operating system. You don't have to be an expert, but this is not the class where I should spend our time on explaining that there is a PS utility and there is a top utility and stuff like that. I'm just going to assume a couple of things and assume that you already are familiar with that. And in case I am saying anything where you think, hey Sander, what is that? Just let me know. I'm always willing to help, but we need to do it in a reasonable way. And when I say in a reasonable way, what I mean is that, well, we should not be spending time on the rock bottom basics. Okay, I did some troubleshooting at the same time. And now I'm in my virtual machine. Yeah. Right, just to show you, this is my virtual machine. Name is Grodon. Of course, I need root access. Oh, I have trouble typing the right password. And in this virtual machine, top is always a nice way to get started. We can see that I have 64 gigabytes of RAM in total. I have 32 gigabytes of swap in total. These are the parameters that matter, but just to impress you a little bit more, I have 8-core CPU. It's a sweet machine that is running Fedora Linux. I just upgraded it to the last version. Just as a warm-up exercise, let's have a look at the memory usage. I'm a big fan of top because I like simplicity. I don't like to go into complicated utilities right from the beginning. So let's have a look at what top is showing us. Top is showing us that we have megabytes memory. Let's call it 64 gigabytes. It's not exactly it. That is because of memory that is used for the graphical driver, which for our convenience, let's just call it 64 gigabytes. There we can see that of the 64 gigabyte, a ridiculous amount of 56 gigabytes is still available. This machine is not really doing anything, and I would have a hard time pushing it to the limits if I wanted to do anything today, but that's okay. If memory is flagged as free, free means that it's not used by anything at all. Then we can see that 1391 megabytes is used. And if memory is shown as used, then it means that it is in use by one of the two main functions that is happening in Linux memory. And when we talk about the main functions, then we talk about application memory, and we talk about the page cache. So what is application memory? Application memory is also known as anonymous memory. Anonymous memory are memory pages that are claimed by applications. You run an application, the application wants to do something. So we can see that the total of application and page cache, the total of memory in use here is 1391. It goes a little bit further than just the application memory and everything else because of the use of the kernel. Then we can see that we have 6284 megabytes of buffers and cache. And hey, I'm just noticing that in Fedora apparently they make a distinction nowadays where the 1391 is really about application and kernel and no longer includes buffers and cache. Haha, that is a nice surprise. And I am kind of happy with this surprise. You know, I'm always teaching classes like this on top of CentOS. And just to be on the safe side, I am using CentOS 8. And obviously CentOS 8 is a somewhat older operating system. And right now I just updated all my Fedora packages. So this should be Fedora 32. And I just noticed that things have changed. That is one of the stories of your life if you are going to be deeply involved with the workings of the Linux operating system. Things do change and you always need to look carefully. And what we just saw is that if you go in unprepared without checking everything on beforehand, well, suddenly parameters are displayed in a different way. That is interesting. I hope it's not going to be too bad, but at the same time, I think at the level that we want to teach these guru classes, we should be able to deal with some of the minor differences. Right, so buffers and cache, 6284 megabytes. What is buffers and cache? Buffers and cache is recently used files. You know that on a computer typically we have a hard disk, no matter if it's a rotating platter hard disk or if it's an SSD disk. The hard disk is relatively slow if you compare it to memory. And in order to make your system faster, Linux will always use buffers and cache. And the idea is that right here I have a 64 gigabytes machine, and Linux is going to use up to everything that is available in buffers and cache if I don't do anything better with it. Is that useful? Well, by any means, it's not useless. Because if I'm requesting access to a file now, then chances are that I'm going to request access to the same file at some point later in time. And then it is convenient if the file is stored in memory. And if really you are doing nothing else with your memory, then, well, what does it matter if you keep a file for 3 months in buffer and cache? Even if it's not used that frequently, it will make your system a little bit faster. Now, we need to distinguish when we talk about buffers and when we talk about cache. Cache is the read and write cache. So we have a read cache. The read cache is you open a document, the document is copied from your hard disk to memory, and the next time you open the same document, the hard disk is accessed from memory instead of from disk, and that makes your experience faster. That is a read cache. There is also something known as write cache. So if you write to a file, you modify a file, the modification is first committed to memory and it's not directly written to the hard disk. You can configure direct I/O in some cases. In some cases that can be convenient, but normally your writes are buffered in memory and they will be written to hard disk at a convenient moment. Now, what does that mean at a convenient moment? Well, that is a tunable. We will figure out that the dirty cache parameters influence the use of write cache, and you can tweak the dirty cache parameters to tell your system how it is doing. It is interesting to figure out the balance between read cache and write cache, and we will talk about that a little bit later today. I'm just still in my introduction because I like looking at my system a little bit more than looking at my slides. Right, the other thing is the buffers. The buffers is mainly tables that are used for anything. File system tables, the TLB, which is an index of memory that is used, kernel level tables and other stuff that is also in the buffers and in the cache. Now the nature of buffers and cache is that most of the buffers and cache is not strictly required on your system. And that means if suddenly a memory shortage would occur, the Linux kernel can make a decision, and the decision is to clear all buffers and cache. And that's a possibility. If the kernel decides to clear all buffer and cache, we have the benefit that that is giving us more available memory, and that allows you to load bigger applications. And it also gives a disadvantage. And the disadvantage is if you clear all buffers and cache, well, in buffers and cache you definitely have files that you have recently used. And the recently used files need to be loaded again. So it's going to create overhead on your system, and it will make your system slower. So even if clearing buffers and cache is a good option to get more available memory, it is not the best option. In most cases. As a rough guideline, I like talking about rough guidelines just to explain what it is all about. The rough guideline is a recommendation. It's not a universal thing that is always true. And in some cases you may have a very good case to have an exception to my rough guideline. That's the whole idea of having rough guidelines. But in my rough guideline, I would say that at least 30% of the total of your RAM should be either free or in buffers and cache. So if you have a system that is really heavily used, then in this case 30%, that means I would like to have like 18 gigabytes in total in free and in buffers and cache. That's a rough guideline that makes sure that you are always on the safe side. Now by the end of this session you will understand that there are situations that you can never obtain the 30%, but I like using these rough guidelines for people that don't really understand what is happening. So it's kind of a trigger. You see that you drop below the 30%, then that should wake you up, and you should start investigating what is wrong. Right, we were talking about the decision that the Linux kernel can make if there is a memory shortage. The decision that the Linux kernel can make if there is a memory shortage at one side is to drop buffers and cache. At the other side is to move memory pages to swap. The thing is that the Linux kernel has a very clear vision on the distinction between active and inactive memory. And if you move memory pages to swap, you can liberate memory. Obviously, you don't want to move active memory pages to swap. But if you have inactive application memory, it's application memory that we are talking about, and you move your inactive application memory to swap, then you obtain something good. And for that reason, my starting opinion about swap is that in general in Linux having swap is good, and even using swap is not bad by default. There are some operating systems that have very bad behavior towards swap, and Linux is just not one of them. Right, I am going to swap to the slide now that we are talking about swap, and you should be able to see my slide mentioning what are the essentials. Everybody good so far? I'm trying to get some message from you at least once every 15 minutes, so I do appreciate if every now and then you post something in group chat. You know, this is an online platform. We had an internet outage today in the city where I am living, and it can happen in an online platform that there is an internet outage and I am not even aware of it. But David, Glenn, thank you very much for confirming that all is okay. Right, you can see a slide now, and the title of the slide is "So what are the essentials?" And yes, David, you will get a copy of the slides. We do a break in the middle of today's session, so that I can get myself some new coffee, or even considering the weather here, I might go for a beer. No, I don't like doing beer, but you will get for the slides during the break, and worst case I will send them later. I know how to find you. Right, so let's talk about the essentials. When I say what are the essentials, these are the starting things that you should know about memory. And I can see somebody else has just joined. Patrick, welcome to this session. We started 20 minutes ago. You missed my introduction, but no worries. I'm recording everything and you will get access to the recording. If anything is unclear, just ask. Right, so I'm on the slide, and the title of the slide is what are the essentials. So these are the topics that we need to understand before we do anything else. First essential is that memory is organized in pages, and the pages are 4 kilobytes by default. I should say kibibytes, but as the kibi and the mebi and the gibi, etc. are the default right now, I just keep it easy and I say kilobyte and maybe a megabyte and so on. And I will clearly indicate if there is a significant difference. By the way, Patrick, you have your microphone open. I would recommend that while I am teaching you keep your microphone closed because everybody is hearing it, and you just open the microphone if you want to say something. Please. You should find something in your interface that allows you to mute you. I rather have you mute yourself than me mute you, because if I mute you, you cannot unmute yourself. Right, another thing that is interesting to know is that processes have a major and minor page fault counter. Page fault counter is telling you something about the performance of your memory. I will explain in detail what exactly these page faults are about. Another thing that's important to know is that systemd can be used to enforce memory limits. In the old days, your Linux kernel was offering memory, and if you would have a 64 gigabyte system, then applications could allocate up to 64 gigabytes in total. Nowadays, we have systemd, and systemd is doing something amazing, and that is the memory resource limitation. Now, I'm saying systemd can be used to enforce memory limits. In fact, it's not systemd. It is a Linux kernel feature that has been around before systemd was even introduced, and that is cgroups. Cgroups is something that I was already playing with a decade ago. And yes, cgroups are a Linux kernel level limitation. Cgroups are very important because you use them in containers as well, and they are about limiting the availability of resources in your environment. And systemd just implements cgroups to allow you to limit, to enforce memory limitations. The fact that cgroups and systemd do that does change the behavior towards memory management a little bit for you as a person. There are just some things that you need to understand. For example, on your 64 gigabyte RAM system, your web server can generate an out of memory condition when it uses 4 megabytes if you have limited the available memory to your web server for 4 megabytes. Right, another essential thing that we need to know about is that Linux uses virtual memory that is mapped to physical memory. We will explore that in detail in the next slide, but virtual memory is not related to anything. It's a virtual address space. A virtual address space that is determined by the number of bits that your CPU is providing to do memory related stuff. Virtual memory, well, it is a lot. If you're looking at a regular 64-bit system, the regular 64-bit system can address up to 256 terabytes of virtual memory. It's an address space. It's an address space that allows applications to claim memory pointers, and they don't do anything with it. It's just a claim. Resident memory or physical memory is the memory that's actually used, and we will investigate that applications very frequently claim a lot more virtual memory than physical memory. This relation between virtual memory and physical memory is important. You should know about it, because knowing about it means that you can better analyze what is going on. We will talk about it extensively. This is just the introduction. Related to that, there is segmentation fault. I just experienced a segmentation fault still on Monday. What is a segmentation fault? A segmentation fault is a condition when a process points to an illegal physical memory address. You know, memory is protected. If one process is using physical memory pages, other processes cannot automatically access these physical memory pages. And if due to a programming fault, a programming error, a process is trying anyway, segmentation fault arises. Typically, that means you have buggy software. So virtual memory and physical memory is one of the things that we need to further investigate. Also, we need to talk about over-allocation. Over-allocation and related to over-allocation out of memory. Because of virtual memory use, over-allocation is standard. Just to give you a quick impression, if I can allocate in virtual memory up to 256 terabytes of memory, well, I have an impressive 64 gigabytes of RAM on my laptop, but that's not 256 terabytes. So it may happen that all these processes that are loaded and have claimed their virtual memory are suddenly starting to claim resident memory. And they can, because over-allocation is a default in Linux. And if that arises, then you easily get in an out of memory situation. And out of memory is pretty bad because if you reach out of memory, then the Linux kernel will kind of randomly start to terminate processes on your system. And that is bad. That is a situation that you absolutely do want to avoid. And last but not least, swap space is cool and swap space is useful. Right, let's start and focus on virtual memory. I have my slides again. Let me swap to the demo system a little bit so that we can change around a little bit between slides and demo. So what do I want to do? Well, we still have top, and that is okay. Top by default is sorting on CPU utilization. I'm using the arrow keys in top 1, 2, 3, 4 times, and now it's sorting on virtual memory usage. And in virtual memory usage, you can see that we have this GNOME shell process, and the GNOME shell process is using 4 gigabytes of virtual memory. And it is only using half a gigabyte, well only, it is using half a gigabyte of resident memory. So the thing that you see here is that processes allocate too much virtual memory. By allocating too much virtual memory, you make sure that you have some working space. It's like putting your towel on a beach on a busy day. You want to allocate a little bit more space so that you can walk around it. Once you have allocated the space, you can also use the space. And that is something by design that is happening in the Linux kernel. So theoretically, my GNOME shell process can grow up to a memory claim of 3.6 gigabytes of memory, because that is the virtual memory that it currently has. And it can grow the resident memory all the way up. We can see that also some shared memory is involved. Shared memory are physical memory pages that are shared with other processes. And shared memory is very useful as a way of IPC. IPC is inter-process communication. Inter-process communication is nothing fancy. It's just defining how processes can communicate to one another. And shared memory is one way of doing it. In fact, I am realizing that my 64 gigabyte system is too cool. And I'm going to show you something else, because I cannot really make my point on a 64 gigabytes system. I am going to connect to, well, I have it right here as a VMware machine. So let me connect to Linfun 0. You should see virtual machine right now. The name of the virtual machine is root at localhost, and you should be able to see the output of the IPA command, just to make sure that you see the same thing as what I am seeing. This interface has a lot, but I do not have a really good window to see what you are seeing. So if you see anything else, please let me know. The interesting thing about this machine is that 3-M is showing me that it just has 1800 megabytes, and it's running a graphical interface as well, and that is so much more useful to demonstrate what is happening memory-wise. So we have 2 gigabytes of RAM on this system, and what do we see? We see in virtual memory we have Firefox claiming 3 gigabytes of virtual memory. We see web content claiming 3 gigabytes of virtual memory. We see GNOME Shell claiming 3 gigabytes of virtual memory, and we see web content claiming another 3 gigabytes of virtual memory. And what does that mean? Well, if you just add the first 4 to one another, then you get already to 12 gigabytes of 12 gigabytes of virtual memory. And how can we have 12 gigabytes of virtual memory on a system that only has 1.8 gigabyte of RAM and 2 gigabytes of swap? Well, we can have that because virtual memory is not real memory. It's not really there. It's just a virtual address pointer. If you want to get more details about that, I warmly recommend one of my favorite files, Proc Mem Info. What do we see in Proc Mem Info? We see detailed information about what is happening in memory. For instance, you can see how the kernel distinguishes between active memory and inactive memory. So the kernel knows which memory pages in RAM are not currently actively being used, and the kernel is capable of dropping these inactive memory pages or of moving these inactive memory pages to swap if that is necessary. We can see statistics like dirty cache. These are files that still need to be committed to disk. They have been written to and they need to be committed to disk still. We see slab memory. Slab memory is the memory that is in use by the Linux kernel. And we see right here VM total. And in VM total, I have kind of a weird size. What you see here is gigabytes, and what you see here it's 32 terabytes in total. That is not really the maximum that can be allocated, but this system, 32 terabytes, is what theoretically it can be allocating. That is the virtual memory that we are talking about. So you have an address space of 32 terabytes in total. And the fact that your processes are not using everything, that is not what matters. The resident memory, that is the next column in top, this column, this is about what is happening in physical RAM chips. Right, let me go to the presentation a little bit. Because after all, I try to summarize the most important things for you. So what do we need to know about a virtual memory? Well, processors use virtual address space. On a 64-bit CPU, the maximum size is 16 exabyte. Just to put it in context, you know what a terabyte is. After terabyte, we have petabyte. After petabyte, we have exabyte, and exabyte, that is 2 to the power of 64. The fact is that processors do not use all of their 64 bits to address memory. They are limiting that down, as we will later see. Now, a very important thing to know about virtual memory is that when the process actually requests memory, the kernel maps the physical address of a page frame to the virtual address in the process address space. So we have a process address space with these virtual addresses, and when you use it, you are starting to claim physical memory. There is a mapping between virtual and physical memory if the virtual memory starts being used. The Linux kernel applies memory isolation, and that means that the process can only access memory that the kernel physically has granted access to. If the process is trying to access other memory, then the process is buggy and generates a segmentation fault. We just talked about it a little bit. Let's talk about virtual memory size. So the theoretical virtual memory maximum is determined by the number of bits that is available for addressing memory in the CPU. And in 64-bit CPU, that gives us the 16 exabyte that we were just talking about. Many CPU architectures reserve specific bits for specific use, and that means that less virtual memory is available. We can actually see what is available, and we can see that if we are going to look at Proc CPU Info. In Proc CPU Info, Proc CPU Info, we need to be looking for, where is it, the address sizes. So right here we can see that the address size of this CPU is 39 bits physical, 48 bits virtual, and that is on my 8-core Intel i7 that we have in the physical machine. So the calculation on this machine is 48 bits in total. 48 bits in total, that is what, according to the Linux kernel, is an older CPU. There are newer CPUs that provide more bits to address memory, and these newer CPUs can address a total of 128 petabyte. You might very well imagine that for your laptop and my laptop, 256 terabytes seems an enormous amount of memory, but if you move to the era of supercomputers, in supercomputers, some supercomputers are going beyond 256 terabytes already. And then it is good that on these computers as well you are capable of using more bits to address memory and increase the amount of memory that can be addressed. Just curious, if you want to test it for yourself, let me know if you have one of these systems that has 57 bits in total. For sure I don't, but maybe you are in some nice corporate data center that has facilities that I don't have on my little laptop, etc. Right, next slide is about memory and paging. So physical RAM is divided into page frames, and the operating system memory uses memory pages to address memory, and the page is the minimum allocatable unit, and by default the page size is set to 4 kilobyte. Process has virtual memory address space. We talked about that, and from the virtual address space the physical memory pages are mapped. And yes, Brian, I will show the slide. Thank you very much for noticing. As I don't see what you see, it may happen more frequently that I'm showing the wrong thing. Please tell me so that I can show you the right thing. Right, so processors can only see their physical memory pages. 32-bit systems, the virtual address space is max to 4 gigabytes. 64, it's a 16 exabyte that we are just talking about, and we have just seen the physical versus virtual memory. And we have not yet really talked about the fact that physical memory pages can be shared between processes. And if that is the case, they count to the resident memory of each process. The reason why that is useful is if you look at the system, like my virtual machine here, you can see that there is resident memory that is in use, and if you are worried about memory usage, you can add all the resident memory to figure out what is happening. Shared memory is also memory that is in use, but shared memory is shared with other processes. So it may look as if you are using way too much shared memory, From what I see here, we come pretty close to 300 megabytes in total, but that is not 300 megabytes in total. It's 300 megabytes that is addressed by all the processes as shared memory. And as process A and process B might be using the same shared memory, it's very difficult to figure out what is unique and what is not. You need to go deeper into memory utilization in case you want to figure out. Right, let me get back to the slides. And on the slides, let's talk about page faults. Now, what is a page fault? Well, it starts from the idea that a process has virtual memory. The process claims virtual memory when it initializes, and when the process starts doing something, it needs access to physical memory pages. And these physical memory pages need to be allocated. If the physical memory page needs to be actually allocated, a page fault is generated. Page fault, that sounds like as if something is wrong. That is not true. It's just an indicator of some activity that is happening. We have two kinds of page faults. We have the minor page fault, which occurs when the process accesses a page for the first time and a new physical page is allocated. Minor page faults, as you understand, are unavoidable. And that is probably why they are called minor page fault. Minor in this case means, hey, you don't have to worry about it. It's just part of how it works. Then there is also the major page fault. Major page fault is a little bit more serious. It occurs if the memory page needs to be retrieved from disk. And that is what's happening when you are accessing swap space. That is what is happening if data still needs to be loaded from disk. And you can actually monitor page faults. And I think I should just be doing that by typing this command. Just give me a little bit of time because I want to put up my notes. It's easier if I don't have to swap around all the time looking for my notes. Almost there. You cannot see that, but that's because it's my notes. These are commands that I don't really want to try to memorize. Let me show you the virtual machine. Virtual machine, oh, there we go. And in the virtual machine, let me use well, Firefox, it's a background process. Oh, it doesn't work that way. Okay, let's do it this way. Oh, Firefox is already running. That's even better. Let me use ps-o pid, comma min flt, comma major flt, comma com minus uppercase C Firefox. And there we can see the PID, Firefox. This is the number of minimum minor page faults that it has generated. Quite significant. This is the number of major page faults that it has generated. And that is fortunately not so much. As I was mentioning, minor page fault you don't care about too much. Major page faults, that is what is happening. Let me also use yum install -y perf. If you want to be able to get some more advanced performance data out of your system, the perf command is perfect. Perf of course stands for performance, so if you use perf stat -e minor faults, comma major faults on Firefox, then we get information, and hey, that is interesting because it's only giving us 4,278 minor faults here. Not sure, oh, that's the wrong command. Not sure what exactly that difference is coming from because 4,278 in no way looks like the minor faults that we are seeing here. I am just guessing that that has something to do with perf gathering data, and being just installed, it does not get too far. Look at that. Now it's giving a different number and 3 major page faults only. Must be something related to a data gathering interval, something like that. I'm not going to explain perf, so I'm not going to further investigate that. Let's have a look at the other topics that we need to talk about. I am going back to the slides, and on the slides our next thing to talk about is the TLB. What is the TLB? The TLB is the translation look-aside buffer. And the translation look-aside buffer is a buffer that is used by your system. It needs to be kept in your memory buffers, so it's consuming memory. And it is a buffer that contains mappings between virtual addresses and physical addresses. So yeah, that's what the TLB is doing. I'm just browsing through the slides, does not add anything interesting. Yusuf is asking, thank you for asking questions. I really like it when people start asking questions. Yusuf is asking when I say the page fault is too high. Well, just as such, it is not really something that you can say, but I think page faults are major page faults. That is what you should investigate. I've never been in a situation where I want to investigate minor page faults, but if I have a system that is heavily swapping, then the major page fault can give you an indication of which processes are swapping, and that is useful information. And then the major page fault itself doesn't allow me to say that it's too high or too low, but it's giving an indication of where the activity is being used. And if next I'm going to analyze my swap and I see that my swap activity is too high, then I relate the processes and I see, okay, I have too much swapping going on, and that is leading to bad performance on my system. So I need to investigate which process it is, and then I'm going to look for these major page faults. By the way, major page faults, that is how we did it in the early days. Nowadays we have a much better way of doing it, and let me bring that up again. And there's a much better way of doing it. Just have a look at the top utility. Oh, I already did this because this is a recycled virtual machine. Look at the last column. The last column is indicating swap usage. How did I do that? I used F in top. F is for fields, and I selected the swap field as well. And as I like this interface, I have written this new interface using uppercase W to the top RC. And what is the idea? The idea is, okay, I see my system is using swap. Half a gigabyte of swap is being used, and that is worrying me. So what am I going to do? Well, in top I'm displaying who is using swap, and I see that GNOME shell is responsible for a significant amount of swap. That is how we do it nowadays, and because this is how you can do it nowadays, you don't really have to investigate these page faults anymore. But this high parameter for swap usage is related to the page faults as displayed by the individual processes. I hope that makes sense. Right, I wanted to show you something else, and that is vmstat. Vmstat, let me do 210. Because we are now talking about swap, and let me just finish this topic. If you see that swap is allocated, you should investigate whether or not swap is allocated actively. And what do we see? If we type vmstat 210, the 2 is for use a 2-second interval, 10 is for use 10 polling loops in total. Here we can see the activity, the swap in and the swap out activity, and I can see that even if half a gigabyte of swap is used, I don't see any significant swap activity, and that's good. So that means that I don't have to worry about swap at all. I do realize that I was drifting away a little bit, but we need to talk about this anyway, so we have done that now. Let's get back to the slides. the slide is about the TLB, the Translation Look-Aside Buffer. So what is the idea? The idea is that looking up a memory page is expensive, and for that reason the Translation Look-Aside Buffer is used. TLB is a hardware cache on your CPU, and that means that it is very fast. And depending on hardware, the TLB cache can be organized in layer 2 and layer 1 cache, differentiating between instructions and data. Typically, layer 1 is an instruction cache because it's very small. Layer 2 is a data cache because it's a little bit bigger. And it caches page mappings that the process has recently used. And because these page mappings are cached, it makes it easier for the process to have fast access to the appropriate memory pages. Now the thing is that TLB is relatively small, and to optimize the use of TLB, huge pages can be used. Now what is the idea of huge pages? Well, in memory, by default, we are using 4 kilobyte memory pages. Okay. Now imagine that you are using an 8 gigabyte Oracle database. How many memory pages do you need to administer in your TLB, in your translation look-aside buffer to manage 8 gigabytes in 4 kilobyte pages? That is 2 million entries. That is a lot. Now we have huge pages, and huge pages are something that you can allocate. You can set them to 2 megabytes, which is the default. You can grow them to 1 gigabyte, which can be useful in specific cases. If you use huge pages, well, especially the 1 gigabyte huge pages, your Oracle database would only have 8 pages to administer, and that makes it very much more efficient to manage these pages. If you want to monitor TLB misses in a system, TLB misses, that is the event where you needed information from the TLB, but the TLB did not have it in its cache. Then you need perfstat -e dtlb load misses followed by your process. This only works on physical machines. This does not work on virtual machines. TLB being a cache that is on memory, TLB is swapping out if a context switch occurs. The visible slide is lab 5a. I shared the wrong slide. Thank you very much, Glenn. Again, I really wish that I could have a preview window in this interface, but I don't. Thank you very much for letting me know, Glenn. So TLB is swapping out if a context switch occurs. You know that context switch is when the CPU is shifting attention from one process to another process, and you can imagine that if the TLB is continuously being swapped out, that's a lot of work being done for nothing. What can you do about it? Well, if you have processes that really are essential, then I would recommend that you pin your processes to specific CPUs. You know, you can do that in recent Linux kernels using CPU set in C groups. So you pin your process to a specific CPU so that you can make in multi-CPU systems, you can make sure that your application has exclusive dedicated access to specific CPUs. And that takes away the problem of the TLB being swapped out at context switches. Context switches are cool if you have single core, but on modern servers nobody is using single core. So take advantage of the fact that multiple cores can be addressed. Right. Next, memory COW, copy on write. This is just a little bit nice to know about memory internals. So new processes are created by forking the parent process. That means that the duplicate process is copied, is created, and pages are marked as copy on write, and that means that data is modified while duplication occurs. So if a child process starts, then a copy is made of the parent and modifications are made to the child. And where data can be shared between parent and child, the child has pointers to read only parts of parent memory address space. That is how shared memory occurs, and it makes it your memory can be used in a more efficient way. And the data is only really copied to the child when it is written to, and that leads to a performance improvement. That is just something that is cool. I can see, oh yes, and that's scary, I can see that two of you are probably doing something else. My interface is telling me if you are in a different screen, so I can see it if you are checking your email. And of course, I'm a person as well. I like doing different things when I take online. Just want to let you know that we will be taking a break in about 5 minutes. Yeah, I'm not going to tell you who it is who is doing something else. That would be too privacy related. But for me, it's an indicator that I need to do something if that's happening. Right. Let's talk about huge pages. So we just talked about huge pages. So huge pages bring the benefit that they make the TLB smaller. And huge pages also make allocating memory easier. And you can set huge pages to either 2 megabytes or 1 gigabyte. That's a system setting. You need to use the huge page size kernel boot parameter. That's a kernel boot parameter, as in a boot parameter that needs to be specified in grub. It's not a proc tunable. You can view the current huge page size in Proc Mem Info. And huge pages must be allocated as contiguous memory, and that may be problematic if memory becomes more fragmented. And you should notice that only huge page aware applications can use huge pages. That is something that I'm going to show you next. For now, I am going to show you a problematic huge page allocation on my low memory virtual machine. So 3 minus m, I have 129 megabytes of memory that is free. Grab minus I huge on Proc Mem Info is showing me that, well, I don't have huge pages at the moment. This is all the huge page information, total free reserved. The surplus, that's something that you don't want to know. The huge page size is set to 2 megabytes, and the huge TLB, that's the translation look-aside buffer for the huge pages. I'm not using any huge pages at this moment. Let me use sysctl. That's something else in systemctl, right? This is how you manage proc tunables using the sysctl mechanism. And I'm using sysctl minus a pipe grab huge, grab minus I huge probably. Oh no, this is not in sysctl. What do we see? We see a couple of huge pages settings. And one of the settings that we see here is VM number of huge pages. Now let me use echo 100 bigger than proc sys VM number of huge pages. And that is trying to allocate 100 huge pages. Now, do you think this is successful? I can give you a hint. We have a total of 129 megabytes of available memory. So allocating 100 huge pages might be problematic. Before I'm going to show you the huge pages, I want to show you that something has changed in the memory allocation. So what has changed? We can see that used is now set to 1292. We have 193, and you can see that the kernel needed to make more space available. So you can see that before it had 480 megabytes available, and now it has 304 megabytes available. And what do we see? We see it has worked on buffers and cache. Before we had 559 in buffers and cache. Now we have 317 in buffers and cache. So what does that mean? That means that I was trying to allocate huge pages. These huge pages need contiguous memory. And the Linux kernel was very short on memory. So what has the Linux kernel done? The Linux kernel has freed some memory. And how did the Linux kernel free the memory? Well, apparently by dumping buffers and cache. And as a result, at this point, huge pages are allocated. And yeah, it succeeded in allocating 100 huge pages. What you should remember about huge pages, if you allocate memory to huge pages, that memory cannot be used by anything else. So if I allocate 60 gigabytes of huge pages on my 64 gigabyte laptop, then I only have 4 gigabytes for the remaining operations. Huge pages are cool, but what you should remember is that huge pages, when you allocate huge pages, these memory pages are not available for anything else. And the downside of using huge pages, and I'm going back to my slides now, the downside is that huge pages can only be used by huge page aware applications. Right, I will do 2 more slides, then we do a 10-minute break and then we will continue. So we should be on our break within 3 minutes or so. So huge page awareness. Double checking that we are on the right slide. You should be seeing understanding huge page awareness at this point. So only processes that use Mmap, shmat, shmget system calls can use huge pages. If you wonder about system calls, you can use strace to figure out if huge pages can be used. And I am just wondering the best way to demonstrate. I don't have a real good way to demonstrate, so let me just do it in the physical machine. I'm using strace -c on ls. Of course, ls is not going to use huge pages. Oh no, I need to install strace. A little bit about system calls. Any application that performs an action is issuing a system call. And in order to get memory, applications can use specific system calls. And what did we see in the slide? Only processes that use mmap or shmat or shmget system calls can use huge pages. And what do we see? Believe it or not, the ls command is using the mmap system call. So ls can benefit from huge pages. But this is definitely something that is not going to work for all of the processes. If you want to know if your process supports huge pages, use what I just did, strace -c to figure out if it can. Look for mmap, that's the most common system call for memory allocation. You will see it there for some applications, but not for all of them. Right, the next thing, and that is on the slides, and yeah, I just realized that it would be really convenient for you if you have slide access. I will take care of that during the break, but I'm not swapping back to the slides just to tell you about 3 lines. I'm just going to read it and demonstrate it. If a process uses mmap, huge pages must be mounted in the huge tlbfs sudo file system. You know, sudo file systems, that's like proc and such. That's a file system interface to do stuff, and that doesn't really exist on disk. Now, if we are on a recent enough operating system, just type mount pipe grep huge, and what do we see? We see that the huge table mount is already there. So huge table fs is mounted on dev huge pages, so it's an interface in the dev directory. The type is huge table fs, and here we have the properties, and the page size is set to 2 megabytes. On very old operating systems like RHEL 6, for example, you needed to make this mount yourself. I can show you how to do that. mkdir/Vugt and mount -t Vugt tlbfs none on /Vugt. So what do? We specify the file system and we specify the device. The device is none here, and that is what we mount on Vugt. I'm not going to press enter because really we do not need this on this system. Right, let me get back to the slides. Last slide that I want to talk about, and that is transparent Vugt pages. Transparent Vugt pages are Vugt pages that are somewhat more flexible. The kernel can automatically allocate them, the kernel can manage them, and the kernel can swap them out. Transparent Vugt pages are cool for specific workloads. Do not use transparent Vugt pages for database workloads. So it's something that you want to manage. If transparent Vugt pages are used, then there is a Vugt page daemon that scans for memory and merges pages into the transparent Vugt pages. And transparent Vugt pages have an interface in syskernel mm transparent Vugt page where you have an enabled file. You can set that to always never advice if you want to manage that. I repeat, do not use them for databases because databases do not deal with transparent Vugt pages. You need the conventional Vugt pages, and databases and Vugt pages go well together. Managing process memory is what is going to be next after the break. That will be a short one, and after that we will talk about the big topic we need to talk about, and it is using swap and cache, because there's so much misunderstanding about swap and cache, and I am going to tell you all about it. Normally I have a break timer. I don't want to waste time to do my break timer. Let's do a quick break. I'm trying to be back here in 9 minutes. I leave my audio open and I will announce myself. I'm going to fetch a cup of coffee. That's the only thing I really need to do. And I need to upload the slides to the course resources. Once I've done that, we will continue. I hope that will be done in 9 minutes. And hey everybody, do not forget to ask questions. I don't see many questions around here, and you are more than welcome to ask questions. So we do a break. Let's try to be back here 1/4 past the hour. I am back. I will work on the slides now, make sure you get them. I am not sure anybody can still hear me. Something has gone wrong in my interface. I am trying to reconnect. All right, at least I have found you again. Can you please confirm that you can still hear me? I have no clue what just happened. Oh, I do have a clue. Hang on. Rearranging my desk. I can suddenly see my control window on top of my Wacom tablet. It's also connected, right? You can still hear me, that's good, and I can see you again. I feel more confident now. If you go to the course materials widget in the interface at this point, you should be able to see my slides. It's the raw PowerPoint format. Sorry for not converting it to PDF. If you have any trouble with the slide, feel free to reach out to me directly. Here's my email address. I will be more than happy to send them to you. Right. I am going back to the slides. You should still be able to see the slides, and we are going to continue and talk about managing process memory first. That's a small topic. Then we will talk about using swap and cache. That's the big topic. So what can you do in order to manage process memory? I'm trying to get this out of the way fast so that we have more time to talk about swap and cache. So you can use your PS command to figure out what has happened. So that's interesting. We have seen it. You can display minor page fault, major page fault. More interesting, you can limit the amount of available memory to a process. If you want to do that, you can use systemd C groups. The easiest way to manage your systemd C groups is by using systemctl set property on your service. sshd.service memory limit is 4 gigabytes, for example. That is what would make sure that systemd cannot address more than 4 gigabytes. And also you can monitor current virtual address space usage using Pmap on a PID or using cat proc PID maps. I'm a cat proc man myself, so I am going to give you a quick overview of what that is looking like. You should see my virtual machine at this point. In the proc file system, we have a PID directory. In the PID directory, every process has its own subdirectory where you can figure out what it is doing. I want to know more about 55150. And in that directory there is a file with the name maps, and if you look at the file with the name maps, we can see the memory mappings. Now, less maps pipe less. Yes, Sander, are you awake? These are the memory mappings where you get information about where exactly specific addresses map to. Most interesting is when we look at this right here, you can see the virtual addresses, and the virtual addresses refer to something physical, and they tell you what exactly is happening right there. You do not see it. That is interesting. Let me try that again. You still see the PowerPoint. Okay. Going back to the PowerPoint, going back to the virtual machine. Can you tell me if you see the virtual machine at this point? You do not. Okay. And what do you see now? Do you see anything? You still see slide only. That is so weird. I just unshared. Now you see nothing. Is that correct? Okay. And now you see, what do you see at this point? You see my terminal. Okay. Then that is where I'm going to continue. Not sure what happened here. But let me get back to proc. In proc we have the PID directory. Let's use 39964. I have no idea what that is. I can use cat on cmd line to figure out, and that is package kit D. And in package kit D we have the file maps, and the file maps is giving information about these memory maps. So if I use less on maps, then I can see the virtual address space, so the virtual address range on the left, and I can see the memory offset of the physical addresses that is happening here. I don't know how readable this stuff is to you. I don't consider it very readable, but what I do consider useful is that, oh, in this virtual address space, it is talking to user libexec packet D, so you can see which application is sitting in there. Alternatively, you can use the Pmap utility, and the Pmap utility is doing basically the same. So Pmap on 39964, and there we can see, let's pipe it through less, you can see the memory addresses, the amount of memory, and what exactly is happening. So we have package kit D that is sitting somewhere, we have anonymous memories, we have libraries, and you can see all the virtual to physical address mappings. To whom is this interesting? Well, this is interesting, I guess, for people that really want to have close insight in what is happening in their memory. Again, repeat my previous point, this is not the most interesting thing to know about. What is much more interesting to know about is swap and related stuff. I am going to share my drawing application this time. Please do confirm if you can see my drawing application so that we don't waste any time on that. You can see the drawing application, that is good. I'm going to finish my coffee now that it's still slightly warm. I'm from the Netherlands, we like coffee in the Netherlands all day long. So what I want to explain is swap, cache, and how all of that works. And I want to give you a graphical overview. Let's say this is my RAM. Well, let's talk about this customer that I had a couple of time ago. The customer was a governmental organization in France. They had a server like 8 GB of RAM on the server. They had 1 GB of swap, and I was observing out of memory. They had lots of out of memory. So I started analyzing what's happening on this server. And what I found, and let me just explain it in terms of memory usage. What I found is that there was a lot of memory in use. Let's just use some, what did I just do? Let's just say that there was 7.5 gigabytes which was in use, and there was 0.5 in buffers and cache, and swap was completely used as well. So 1 gigabyte in use. So the customer was complaining. I can imagine he was complaining. The users were complaining, and it was a disaster. Now, what did we do? We started analyzing, and while analyzing, I had a look at Proc Mem Info, and in Proc Mem Info, I was looking at the relation between active and inactive memory, and I was looking at that relation for anonymous as well as file memory. Anonymous memory is your application memory, file memory is your cache. And what did we see? We saw that file memory was 100% active. There was no inactive file memory, and we saw that anonymous memory, let's just use some values to make the story easy to understand. It had 2.5 as active, and it had 5 gigabytes as inactive. I hope you can imagine that this was a very easy fix. What was happening on this system? Well, this system had no swap. This system did have Java applications, and in the Java applications it is notorious for using lots of anonymous memory, allocating lots of anonymous memory, and leaving lots of anonymous memory as inactive anonymous memory. So what did I tell my customer? I told my customer we are going to apply a hotfix, and the hotfix is we are going to increase your swap space, and I want to increase it to 16 gigabytes. So we blew up the swap space up, and in the end he had 16 gigabytes. And what did we do? We used the Swappiness parameter. The swappiness parameter is one of the most important parameters because you can use the swappiness parameter to tell your system what it should be doing. If you give it, it has a value between 0 and 100. A low value is is telling your operating system that it should drop cache in case it needs more memory. A high value means that it should move as much memory as it can to swap. So I set swappiness to 70, and then we went for a coffee. And after the coffee, what happened? Well, we came back and we had 2.5 gigabytes in memory. So more than half of memory was available. The buffers and cache had climbed up to, let's say, 4 gigabytes. It always takes time for buffers and cache to build up. And yes, now we saw that of the 4 gigabytes, there was 3.5 gigabytes was inactive and 0.5 gigabytes was inactive. And everything else, we had 5 gigabytes of inactive memory sitting in swap. And what happened? All the customers suddenly were happy. What do we learn from this story? From this story you learn that in your RAM 2 things are happening. You have your application memory, you have your file memory. We also learn that if you are running out of memory, you need to do something with your inactive memory. What are you going to do with your inactive memory? That depends. You are going to analyze, and to analyze you have a look at Proc Mem Info. Proc Mem Info will tell you what you have as inactive anonymous memory. Inactive anonymous memory is what you can put to swap. And to tell your kernel to favor moving data to swap, you trigger the swappiness parameter. The other alternative, that's the alternative that we did not encounter at this customer site. The other alternative would be inactive file memory. And what are you going to do if you have inactive file memory? Then you are just going to use the drop caches parameter. And I will show you how to monitor all of this here so that you really understand what is happening. I think this is the most important thing that everybody should know about memory usage on Linux. From this story, we can already conclude that having swap on Linux, in most cases, there are exceptions, but in most situations, having swap is something that is very good for your system. Right, I am going to leave the drawing application right now. If you like the drawing that I'm making, it will be in the recording obviously, but maybe you also want to make a screenshot, you never know. Let me make a screenshot as well so that in case you want to have it later, you can drop me an email and I can send it to you. There we go. Right, so what are we going to do now? We are going to look at a couple of these parameters. And in order to do so, I'm going to make another attempt to get back to my virtual machine. Can you please confirm that you can see the virtual machine? Thank you very much, Glenn. So first thing that we are going to do, I'm skipping the, well, we can have it on screen as an overview. 3 minus m. 3 minus m is the total image of the memory. The important parameter is grab active on Proc Mem Info. And what do we see on this system? The important parameters are right here. We have 371 megabytes anonymous memory that is active. We have 439 megabytes of inactive anonymous memory. We also have 127 megabytes of file and 109 megabytes of inactive file. So what can we win in our memory situation on this system? Well, we can win by moving 439 megabytes of memory, of inactive anonymous memory currently sitting in RAM. We can still move it to swap. We can also drop the inactive file memory to make another 100 megabytes available. That is the analysis that you should do. This analysis relates to what you see in RAM, and yeah, it relates to what you see in RAM. It's not about what you see in swap, because that's a different parameter. You just want to know how much can I still move to swap. So on a clean system, where no swap is being used yet, the calculation is very easy. Have a look at your memory usage on an average day on your clean system. If no swap is being used yet, the total amount of inactive anonymous memory is what you should have available in swap. Now I am going to try to influence this process. I'm not even sure if this is going to work, but hey, we can at least try. So sysctl -a pipe grep swappy. That is giving me the VM swappiness. VM swappiness currently is set to 30. I am going to use echo 90. That is very aggressive. I would never use 90 in real life. In real life I would go up to 70 and not much higher. 70 is clear enough. So I'm using echo 90 greater than /proc /sys/vm/swappiness. And now if I do my sysctl -a grep swappy again, we are going to have a look at free -m and see if anything changes. Well, nothing is changing apparently, and I guess the reason that nothing is changing is that the kernel already did a pretty good job in optimizing region number 2. It always takes a little bit of time if anything is required. The other thing that you can do, you can drop inactive file memory. We can see right here that we have 127 inactive and 109 in inactive. This is about the value that you see in buffer and cache. Let's try to understand clearly what is happening, because 127 plus 109 makes 236. I see 339. That means that we have another 100 megabytes, which is a significant amount, that is using by the different tables. Let's keep that in mind. Let's have a look at these tables a little bit later. Let me go to proc sys VM. In proc sys VM we have a parameter drop caches, and if I am using echo 3 to drop caches, then I'm typing free -m again, and it is dropping inactive cache. So I should not do free -m. I should be better off using my grep active on proc mem info. And what do we see? We see that we still have 43 megabytes of inactive cache, but that's significantly lower than the 100 and something megabytes of inactive cache that we had before. There are different values that you can echo to the drop caches file. Echo 3 is the most aggressive value. Look up these values in the kernel documentation for their exact meaning. But if you want to experiment with this, just use echo 3. Notice that this is not something that you should do yourself on a very regular basis, because you have a kernel doing an excellent job taking care of that. I just wanted to show you how to trigger this. Oh, we were talking about the difference between what we have in buffer cache right here, 227, and what we see right here, 135. That's about 100 megabyte difference. That should be visible if you use SlabTop. SlabTop is about slabs, and slabs is about kernel structures. Is there anything that you can do about your kernel structures? Not that much. Well, the only thing that you can do, if it really is becoming very bad, you can have a look at what exactly is it doing, and at the moment that you recognize something, you can try to optimize it away. For example, right here, we see a reasonable amount of 8 megabytes for XFS inode. That's your XFS file system. all file systems have an inode table. Right here we can see an inode cache, 17 megabytes. Okay, that is still acceptable, I guess. But if you see something that is very high, then you can always try to use a different file system, for instance, or to reorganize your file system. The main reason why your slab might grow extremely high is because of file systems, and if it's because of file systems, you should be organizing your file systems in a more efficient way. And for the rest, Slab Top is not the most readable utility, but it's a cool utility. It allows you to monitor what is happening in kernel space. Right. That was a demo I wanted to start with. Let's have a look at the slides for the additional details. I'm switching to the slides right now, and you should be seeing the slides using swap and cache. I don't like teaching by the slides, so if you are worried, oh, we only have 25 minutes, not even 25 minutes left, and we still have 23 slides to do, is that bad? No, that is not bad at all. I'm using the slides just to summarize some stuff. So this slide, understanding memory usage, summarizes what we have seen in the drawing. Now, one thing, oh no, I already told you, make sure that for your buffers cache plus 3, on an ideal situation, you should always aim at having 30% of your memory for buffers cache and free. Now, understanding swap usage. I want to go over this anyway. Linux kernel can page out unused memory pages that have been allocated to make place for other memory pages. That is good. That is the story about inactive memory that we have just talked about. When the paged out memory is needed again, a major page fault arises and it will be paged in. We talked about that. Major page faults indicate swap activity for specific processes. Major page faults are not good. The main point that you must remember from this session is that using swap is not bad by itself, but it should be used for inactive memory only. And if swap is starting to be used heavily, you will suffer a severe performance penalty. Depending on the quality of your storage, if you have very fast SSD, it's still 100 times slower than your RAM. So try to keep your important data, your file, your application memory in RAM as much as you can. We have also seen how you can monitor swap usage in VM stats. Look for SI and SO. We have talked about this. We have not talked about this. Understanding a required swap space. Now first thing to realize is that you will find very different recommendations. So I have just used my own observations and made my own recommendations. What are my recommendations? Well, if you have less than 2 gigabytes of RAM, make sure you have 2 times the amount of RAM. If you are in swap, that is. If you are between 2 and 8 gigs, use equal amount. If you're between 8 and 64, use 0.5. If you're beyond 64, it really depends on your workload. Now we have seen that you can swap, you can tune swap behavior using Swappiness, but also using VM min 3 kilobytes. What is VM min 3 kilobytes? Well, that is a parameter that is showing you how much memory you want to keep available at all times. If you set that higher, then your swap will be used sooner. So let's try to monitor this one on the virtual machine. If you do not see my virtual machine, please let me know. sysctl -a pipe grep. By the way, I think I can also do this without the -a and the grep, but this also works, so who cares? There we can see that the minimal amount of kilobytes that should be available is, let's call it 42 megabytes. And do we have the 42 megabytes? Well, at this point we definitely have the 42 megabytes. If you want to make sure that you always have a certain amount of RAM available, push this limit up. But if you push this limit up, then your swap space will be used faster. Switching back to the slides, you should be seeing my slides at this point. Right, page cache, we talked about that. Optimizing page cache. These are interesting parameters. Page cache, that is about the cache parameter. And as I was telling you, cache can be used for reading and for writing. We have just seen VM drop caches. VM drop caches allows you to drop what is currently in cache. But there are some other parameters that are very interesting as well, and these are the dirty parameters. So let me get back to the virtual machine again. If I'm using my sysctl-a grep dirty this time, then we can see the vm.dirty parameters. Now what is dirty cache? Dirty cache determines the interval to wake up the flush daemons. Dirty cache is about data that has not yet been committed to disk. So it's still sitting in RAM. The longer you keep your data in RAM, the more RAM it consumes. So it's bad for RAM performance, but it's good for write performance, because if you keep data in RAM longer, you can have more efficient writes, and you can influence that process using the dirty parameters. The important parameters are the write back centisecs. Centisecs is 100 of a second, so 500 centisecs is 5 seconds. And that determines how often the flush daemons should wake up. And then there is the dirty expire centisecs, which is defining when dirty cache is eligible for being flushed out. And by default, that is 30 seconds. You want to optimize your writes at the expense of your memory usage, make it higher. You want to make your commits to disk faster, which will give you better memory usage, especially on write-intensive systems, make it lower. Just a side note, most people optimize by making this limit higher. Making lower is in general resulting in increased activity on your system, so that doesn't necessarily make everything better. You should be seeing my slides again. Right, let's talk about swap. First thing to know about swap is that you should put your swap on SSD. There are two reasons for that. Reason number one is that SSD is simply faster. Reason number two is that SSD can be addressed directly. You don't have rotating platters where you need to make sure that the disk head is at the right location of your rotating platter. So use SSD for swap. If you are using cheap ass SSD, then you might have the problem that your surface is wearing out sooner, but if you use server grade SSD, then it shouldn't be a problem of the SSD cells being damaged by using it too much. Next thing that you can do if you are using swap a lot, MK swap can be used to create your swap devices. If you use MK swap, use swap devices. Do not use swap files. Consider swap files a temporary solution. Like my customer in France, I used a swap file. It was a perfect temporary solution because he was having a big problem. We needed to fix it immediately, and then you can allocate a swap file. But for good performance, swap to devices. And also consider using pry equals something. Pry equals something allows you to set priority. If you have faster devices, they should have a higher priority. If you use equal priority, then your swap will be load balanced between all of your devices. So David is asking, thanks for asking question, David. Will that only be relevant for physical devices and not VMs, as in an ESXi host with regards to SSD? Well, yes, because if you are creating a virtual machine, you don't directly allocate SSD, you allocate it indirectly. So on virtual machines it's not that important, but in a virtual machine it depends, of course, how you created your virtualization layer. And I think that the virtualization layer should also be on SSD and not on rotating platter anymore, because if the virtualization layer is swapping out to your rotating platter, this principle also goes for VMware, because it's a disk limitation that you need to put the disk head at the right location of your rotating platter disk, and it's a disk advantage that you don't have that if you are using SSD. So thinking about it, in Linux, of course, it doesn't matter anymore in virtualization, but you bring the problem one level higher. Right, finding memory leaks. This is a thing that I am just going to do quickly because there's more important stuff. Now I'm going to do it differently. I want to talk about ohm. Managing ohm. Ohm is important. We have 13 minutes left and we might skip the two geek things, but we need to talk about ohm and about overcommitting. I consider that essential. So what is ohm? Ohm is not your uncle. That is a Dutch joke. I think we have one person from Belgium. If you are Flemish, and we have one from the Netherlands. Ohm is Dutch word for uncle. Ohm is out of memory. And as most applications never use their entire address space, Linux uses memory overcommitting. Memory overcommitting is good. Because it allows you to use memory more efficiently, and it allows you to run more applications on a Linux system without the memory being physically available. But the downside is that you might get yourself in an ohm situation. Now, what about the ohm situation? Well, ohm situation occurs when a minor page fault happens. So it needs to read in data in RAM, but no free pages are available. And if ohm happens, the ohm killer becomes active and it will kill one or more processes to free memory. And that sounds like such a stupid situation, but it's the only thing that the Linux kernel can do if you have agreed that memory over allocation is good on beforehand. Now, the ohm killer becomes active and will kill one or more processes to free memory. This is, of course, leading to an unreliable system, because if you randomly shoot down processes, you get a very unreliable system. You don't know what is happening anymore. Even if there is an ohm score that allows you to increase or decrease likeliness of certain processes to be killed, even if the kernel and systemd are exempt from this process, it's still very bad if this is happening. And for that reason, I like having VM panic on ohm, the proc tunable, and I like setting it to 1, because what will that do? It will give you kernel panic. You know, the problem with the ohm killer is that your system is becoming unreliable. Unreliable systems may lead to data loss. Data loss is bad. I rather have one dramatic moment where my system is going to crash and reboot so that everybody knows that something bad is happening than having this unreliable system. And that is what you can accomplish using VM panic on ohm and setting it to 1. Obviously, it's up to you what you want to do there. Now, it is nice you can trigger what's happening using ohm. So I am going back to my virtual machine. I'm expecting you to see the virtual machine at this moment. And I am going to do an echo h greater than proc sysrq trigger. Echo H is sending help to the sysrq trigger. The sysrq trigger is a magical key sequence that you can use. If you want to see what exactly has been done, you type dmessage, and dmessage shows you the help that you have just requested. It's kind of a different approach than using man, but this is how it works in Proc sysrq trigger. And you can see that you can do many very bad things using this Proc sysrq trigger. Like you can crash your system if you want to, which is amazing if you are preparing your system for disaster and you want to test your disaster recovery solution. Isn't it cool that you can just crash your system? I mean, we have Windows that is doing it at random moments. In Linux you can control the crashes yourself. I think that is awesome. But let's not talk about crash, let's talk about ohm here. I am going to use echo f greater than /proc/sysrq trigger, and oh no, do you see that? I am being kicked out of my graphical interface. Why is that? Well, that is because I started an ohm trigger, and the ohm trigger is going to randomly terminate processes. Now, if I'm using term, and in term I am opening root terminal again, there we go, and I am using less on var log messages. There will be a day, I promise, that I will by default start using this journal CTI, and I think if we look for ohm, there we go, manual ohm execution. So what happened, we can see what has happened, and we can see that well, if you read all of this, you should also be able to see what exactly has been killed by the ohm trigger. This is how you can recognize your out of memory situation by any means. And this is something that should not be happening too much. But I think it's kind of cool to at least see what is happening if you are reaching an ohm situation. Okay, back to the slides, because we need to talk about how to reasonably deal with ohm. One solution is to use ohm score. Ohm score is a setting, and the setting is in proc PID ohm score, where PID obviously is the PID of the process in question. A higher ohm score is more likely to get killed. Kernel and systemd are immune, and root processes with a higher runtime and processes involved in direct hardware access get a lower score. So by default, the mechanism is thus that the risk is limited. But you can use proc PID ohm adjust, and ohm adjust takes values between -17 and 15, and you can use these adjust, write these values to proc PID ohm adjust to increase or decrease the chance that your process is ever getting killed by ohm. But hey, why would you optimize your system for the situation where ohm is going to happen? To be honest, I think that the default approach is fair enough to decrease the chance of root processes, processes with a higher runtime, and processes in direct hardware access to be called. I think you better think about avoiding ohm. Now, how do we avoid ohm? We avoid ohm by making sure you monitor your hardware and also by managing memory overcommit. Now, what is overcommit? Well, as processes allocate virtual memory that often goes unused, the kernel allows overcommitting of memory. You know, if all of these processes claim 1 gigabyte of virtual memory and they only use 5 megabytes, then you can easily allow your processes to claim up to 100 gigabytes of virtual memory, even if you just have 2 gigabytes in your system. because physical pages are only allocated when memory starts being used. It's like overbooking in the air, you know the good old days that we could still hop on airplanes and go fly anywhere. They sell more seats than is available on the aircraft, and in most cases that goes well. In some cases it doesn't go well, and you need to deny boarding to a passenger, which is the more friendly alternative to an home kill in real life. So memory overcommitting is something that is essential in some environments, especially virtual machines. In virtual machines we have KSM, kernel same, I don't remember what it stands for. The approach where you are doing memory deduplication because all of these virtual machines are running the same kernel. So why do you want to run it 100th time if you can do it one time only? That is something that makes overcommitting possible, and that makes it the Linux kernel can deal with overcommitting. So overcommitting by itself is good, especially if you know that the Linux kernel is doing a pretty decent job in memory deduplication. But overcommitting does involve a risk, and the risk is that your uncle will visit you or ohm will occur. You should consider, if you are frequently getting ohm situations, I already made my Dutch joke on another slide, you should consider tweaking the overcommit memory parameter. I think this is a very important parameter. VM overcommit memory. You have three different options. Option number 0 is heuristic overcommit. That is the default. And that means that the Linux kernel is going to allow overcommit unless it is a very large unrealistic request. Option number 1 is a stupid option, always overcommit. I have never seen a situation where it was necessary to use option number 1. I have seen a situation where it was advisable to use option number 2. That is the ratio-based overcommit. Now, how does it work? Option number 2 in VM overcommit memory takes the available amount of RAM plus swap plus the percentage in VM overcommit ratio. VM overcommit ratio typically is set to 50%. So what does that mean? That means that if you have 2 gigabytes of RAM, 2 gigabytes of swap, you can overcommit up to 6 gigabytes. If you want to be able to overcommit up to 12 gigabytes, then that is possible. Just use VM overcommit ratio and set your VM overcommit ratio to 200, which means that you can double the amount of RAM and swap. Now, what I like a lot is the option to monitor your current memory availability, or that's not exactly how I should say it, to monitor the estimation of what your kernel thinks is needed on this system given the current workload to avoid overcommit. And this is something that you should be doing today on all of your servers if you are responsible for managing servers. That is grep committed on Proc Mem Info. And what do we see? We see committed as it is recommending that this system has 6.4 gigabyte of RAM to avoid an overcommit situation. Hey, if I use 3 minus M, what do I see? I have 4 gigabytes of RAM only. And my system is recommending me to increase the workload to 6 gigabytes, 6.5 gigabytes even. So what can I do? Maybe in this case, I should just increase my swap space to avoid the overcommit situation from happening. And that is how you can manage overcommit. And that is also what brings us to the end of the 2 hours. Wow, with that we are at the end of our first ITGilde Guru class on Linux memory management. I want to give you the opportunity to ask questions. So if you have questions, let's do a few minutes for questions. If you have any, post them in the chat please, and I will answer them. And if you do not have questions, then I do have a question. It's more than likely that either Brenda or Anne Rose will send you a follow-up email to evaluate what you thought of this class. We want to know if you liked it or not. The idea behind this class is that we think that for the basic educational needs, people go to learning.o'reilly.com or one of the competitions. They take an annual subscription and they can get an R8 CSA course included in their $500 annual subscription instead of paying $3K to Red Hat for 1 week, of course. We do think that educational needs still exist for advanced topics like this. And I'm happy to see that we had 7 people in class today because that kind of indicates that you might agree with that as well. Anyway, I'm happy you were here. You will get a follow-up email message with access to the recording. We need to see how to distribute the recording, but we will find a solution. If at any time you have feedback you want to share with me directly, feel free to reach out. I'm typing my email address again, and I don't see any questions coming in anymore, so I am just considering this. You have no further question, so I would say thank you very much for being here today, and I hope to see you again in one of my future ITGilde Guru courses. Oh, and one thing. If you have a suggestion for something you would like to see me teaching in this concept, this is about these nice and interesting features that are not going to attract the big masses that I need to have on the O'Reilly platform. If you have any suggestions, do let me know. Again, thank you very much for your support. I'm wishing you a very nice rest of the day, and bye-bye everybody. I'm going to end the session right now, and I'm looking forward to hearing from you again. Bye everybody, and thanks again.